Hey everyone, and welcome to another Explainer. Today, we are tackling something that frankly feels like pure magic sometimes, but is actually just a total masterpiece of human engineering. We're talking about computer networking. Look, if you have absolutely no idea how to navigate networking, you are in the exact right place. This Explainer is specifically designed as an aid to teach you from the ground up. We're going to demystify all those complex mechanics of how computers actually talk to each other. And we're going to do it by doing something incredibly simple. We're just going to follow the journey of one single message from your device all the way across the globe and back again. Let's get into it.
Okay, so here's our roadmap for today. We'll kick things off with the first connection, move right into finding the right address, then we'll check out the rules of delivery. After that, we'll talk about managing traffic jams, and finally wrap up with planning the road trip. Don't worry, we're taking this step by step.
All right, part one, the first connection. Let's look at where it all began.
To really get some perspective here, we actually have to travel all the way back to the early 1960s. There was this visionary guy named J.C. Licklider, and he and his team pulled off this truly groundbreaking experiment. They connected just two computers, and they did it over a totally standard dial-up telephone line. That's literally it, just a simple phone call between two machines. But that humble little experiment proved that remote communication was actually possible, and it laid the absolute rock-solid foundation for the vastly more complex, layered global internet protocol stack that we all rely on today.
Now, to make these connections actually happen in the real world, you need hardware. And these different devices operated different levels or layers of intelligence. So down at layer 1, we have hubs. Think of a hub as basically a blind megaphone. It just shouts electrical signals to absolutely everything connected to it. Moving up, bridges are a little bit smarter. They operate at layer 2 and look at MAC addresses to just direct traffic locally. But the real brains of the whole operation? Those are the routers. They sit at layer 3 and they intelligently direct traffic between entirely different networks using IP addresses.
Moving on to part two, finding the right address. Let's get this message prepared.
So the whole journey really starts with the domain name system, or what we usually just call DNS. Basically, DNS is the internet's phone book. I mean, imagine if you had to memorize some random huge string of numbers like 142.250.80.46 just to look up a recipe online. It would be a complete nightmare, right? So instead, DNS steps in and translates human-friendly names like google.com into those numerical IP addresses. That way, the routers know exactly where to send your data without you having to do the math.
Okay, so once the destination is known, the data actually has to exit your app. And it does this through something called sockets. You can think of a socket as a literal door between your app and the network. But to get through this door, you need some ID. If your app is using a really simple protocol called UDP, it just needs two pieces of info, a destination IP and a port. But if it's using the more complex TCP protocol, well, it needs a whole four-piece combo. It needs a source IP, a source port, a destination IP, and a destination port. This is absolutely crucial so it can perfectly track that one specific, unique connection out of the thousands of others happening at the exact same time.
Now, the actual journey out that door is called encapsulation. As your message moves from your app all the way down to the physical wires, it gets wrapped up chronologically at each of these 5 layers. So the transport layer slaps on a header with the ports, then the network layer adds the IP addresses, and so on. It's honestly exactly like putting a letter into an envelope and then putting that envelope inside a box and then packing that box into a massive shipping crate. And as you might guess, when it finally reaches the destination, the exact reverse process happens to unpack it all.
All right, on to part 3, the rules of delivery. Time to choose your transport.
So here we have the ultimate beginner showdown between your two main transport options. In one corner, we have UDP. UDP is your reckless speed demon. It's connectionless, it's incredibly lightweight, and honestly, if some data gets corrupted or lost along the way, it doesn't care. It just drops it, which makes it absolutely perfect for things like live video streaming or gaming, where speed is basically everything. But in the other corner, we have TCP. TCP is the careful, super reliable courier. It actually requires a formal 3-way handshake just to get started. It carefully corrects any errors it finds, and it guarantees, literally guarantees, that every single packet arrives in the exact order it was originally sent.
Next up, part 4, managing traffic jams. Let's see how we keep the network moving.
TCP really acts like a brilliant traffic cop, and it uses two completely distinct mechanisms to do it. First up is flow control, which is all about protecting the receiver. It physically stops the sender from just completely overflowing the receiver's limited memory buffer. Congestion control, on the other hand, looks at the bigger picture. Its job is to protect the entire network from just collapsing under too much traffic. So TCP is constantly calculating a safe window of data size for both of these, and it smartly limits its sending speed based on whichever of those two windows happens to be smaller at the time.
But here is a truly fascinating question that network engineers eventually had to solve. How in the world do we avoid network traffic jams on our modern, incredibly high-speed, long-distance fiber optic connections? You see, older algorithms used to just count the round trips of data to gauge the speed, but on a super-fast modern connection, just counting round trips is way too slow to actually efficiently fill all that massive available bandwidth.
Well, the modern answer to that problem is TCP/cubic, which actually happens to be the default algorithm in systems like Linux today. Instead of sitting there counting round trips, TCP/cubic uses a mathematical curve based on real elapsed time. Think of it kind of like smoothly pressing down on a gas pedal. It aggressively ramps up the speed to find whatever bandwidth is available, but then it eases off very cautiously right as it hits the network's limit so it can stabilize. Because of this, it doesn't constantly cause massive data traffic jams. Instead, it just gracefully rides the exact edge of the network's maximum capacity. Pretty smart, right?
Finally, we arrive at part 5, planning the road trip. Let's navigate the globe.
Let's take a look at how a path is actually built. A lot of people tend to confuse routing and forwarding, but it helps to think of it this way. Routing is the really complex, network-wide intelligence. It's like sitting down at your kitchen table and planning out your entire cross-country road trip on a map. Forwarding, on the other hand, is the fast, localized action. It's that split-second decision you make to turn left or right at one individual intersection. So routers do all the slow, complex math of routing in the background, specifically so they can do the lightning-fast job of forwarding your packets in real time.
So how do routers actually learn these paths? Well, there are two main ways. First, we have link state algorithms. These require every single router to broadcast its connections to everyone else, building a complete, centralized, global map of the network. It's incredibly precise, but it's really heavy. Distance vector algorithms, however, are completely decentralized. With these, routers only talk to their immediate neighbors. It's honestly a lot like gossiping over a fence about the best path to take. It's much simpler. But there's a catch. If bad news travels slowly, routers can actually get trapped in what's called a count-to-infinity routing loop, where they are just endlessly passing packets back and forth in a circle. No way, you want that.
Now, networks have a surprisingly relatable way of handling external traffic, and it's called hot potato routing. And yep, it is exactly what it sounds like. A network wants to get foreign traffic off of its own wires as fast as physically possible to save its resources. So it literally drops the data at the exit point that has the lowest internal routing cost. It's like dropping a literal hot potato. And ironically enough, that cheapest exit point might not actually be the exit that's geographically closest to the destination. It is entirely about minimizing the network's own internal burden.
As we trace the final steps of our message here, we arrive at the absolute golden rule of the internet, the end-to-end principle. And this really reveals the brilliant simplicity of the whole system. It basically means that the core of the internet, those massive routers and cables connecting our continents, is kept remarkably simple. They're essentially just dumb pipes rapidly forwarding packets. All of the really brilliant stuff, the error checking, the congestion control, the connection logic, all of that actually happens right on your device, at the very edges of the network.
Which leads us right to our final thought. If the core of the internet remains this wonderfully simple, what incredible new applications will you build at the edge? You see, by keeping the center so simple, the internet allowed for literally limitless innovation on the devices we hold in our very hands. Hopefully, now that we've followed the journey of a single message together, you have a much better grasp on these networking foundations, and you feel empowered to really go out there and navigate the digital world. Thank you so much for joining me on this explainer today, and keep learning.